Hello, so today we are doing this problem called Maximal Square, and the problem is says that we get a 2D binary matrix filled with zeros and ones, and we want to find the largest square that contains only ones, and we want to return this area. So for example, with this matrix here, we have the largest square, notice square, so the sides have to be equal, is this one of size 2. And the problem asks us to solve this. So the first thing we can think of is, let's just think about a brute force solution, right? First, then we can try to improve it. So brute force solution. So the first thing we can do is just like consider every point, consider every cell as a top left corner of a possible square of only ones. So base of a square, pretty much. So we will just go through the cells like this and just consider this one as the top left corner of that square. So if you have a square like this, let's say. So if we have a square like this, well, just consider this one has size 3. And so the top left corner will be here, right? So that would be what we consider. So these are the points. So we'll consider every point as a top left corner of a square. And then try all the sizes, possible sizes that have that point as the top left corner. And so try all possible squares that have let's say, consider every cell X that have X as the top left corner. And so basically consider all possible square sizes, right? So for example, try all squares of size 1, so that would mean only this one. And then try all squares of size 2, that means this one. For this point here, it's only this square. And those of size 3, that would be this one, this one, and has also this one in it. And then for each one of them, for each, check if it's a valid square, which means basically that contains only ones, right? And if it's valid, have, for example, let's say we have a variable max length of square basically. If it is valid, then we do max length would be now equal to max of that max length and the size of the square, right? So very much brute force. And that's pretty much it, right? Just normal brute force. So the one thing that to think of is, well, if we are here, we can take squares of size from 0 up until the length of the length of the matrix, of the row of the matrix. But if we are here, since it's the top left corners, we shouldn't go backwards. We can only take up until, so we can only take of length 1, 2, and 3. And since it's the top left, we can only go to the bottom, so it's only size 1, size 2 when we're going here, and then size 3. And so that's just reduces the search space, of course, for each point that we consider at the top left corner. And so let's code that up. So first we have the max length that is equal to 0, and let's just have some variables that keep track of the number of rows and the number of columns. So we have a length of matrix, and we have the number of columns, and we need to check. Let's just check them to safeguard against this size of 0. So that would be if length of matrix equal to 0. In that case, we can just return 0, right? There is no square to check. Now let's just do our algorithm, which is considering every cell. So that means let's go through rows and for G in. So now we consider every point as the top left corner, and now we consider all sizes, right? So this is 1, and this is step. So let's say this is 1, this is 2, and so this is 1. We just did the first one. Now we do 2, which is check all sizes. So the sizes is for size in range of. So the size, if the point is here, since we are checking a square, we can check only this one that ends here and has this part, because a square we can't have more than 2, and so we can't take 3 on the column because it has to be a square, and so it has to be, the size has to be the minimum of the 2, so it has to be the min of, it has to be limited by the min of both I and j, right? And so that would mean, but it's the part that is here is, so if this point here is at I, let's say here we are at I, and let's say we are considering this point here, this one. So its I is this one and its j is this one, right? So that means that to get this portion here, that's rows, which the number of columns, the number of sorry, its I is here actually. This is I and this is j. So the remaining part here, that's columns minus j plus 1, right? Because let's just try it with an example. So 1, 2, 3, 4, and 0, 1, 2, 3. So for this j here at 0, and the columns here, they are equal to, in this case we have 5, and rows we have 4, right? So the remaining are 2, right? So that's columns, which is 5 minus 3, 5 minus 3, that's 2, right? So that's the number of the remaining ones. And so to get there, because Python, the last, when we end at +1, it will end at columns minus j. So we would have to do columns minus j plus 1, just for the range here to take columns minus j into account, right? And then the other part is for the row, which is the remaining rows, which is this one and this one, this one, this one, this one, and so basically, but with this point, it's only this one, and this one. That's rows minus I plus 1. So the same, but for rows. So that's rows minus I plus 1. And once we have the size, we need to check if it's valid. So if is valid, the square can be identified by the top left corner and the size, right? So if it's valid, now we can say that max length is equal what we said here, basically. And so that would be max of max length and the size of the square, which is this. And at the end, we can just return the area, which is max length multiplied by max length, since that's the area of the square. So now we need to implement is valid square to check basically that, that the square contains only ones. And so we can define that here. So we have the top left corner and we have the size. So we just go through all of them. So in the range of, so we need to go from I to we need to go from I to I plus size, and we need to go for, and we need to go for y in j to j plus size. And so from there we need to check that there is no 0 there. If we find 0, then it's not valid, so we need to return false. So that would mean matrix xy is equal to 0, turn false. And if we continue and don't find any sum that is equal to 0, that means we have only one, so we'll return true. And that's pretty much it. Okay, let's just try with a couple of other test cases. So first, just a couple of edge cases to test against. Let's see. So we have 0, 1, 4, 0, 1, 4, okay. It will probably get time limited exception, yep. Yep, but we are only like one case away from having an accepted solution. So it's a pretty good solution, but it's terribly inefficient. Why is that? So let's look at the time complexity here. So here, this is O of rows. Here, this is O of columns. And then here we have O of, at most, it will go up until columns and rows. So, and since we are doing the min, so at most it will go through min of rows and columns, right? And then we have this function that is called, and this, since it goes up until size, the worst case, it will be starting from here and going for the entire size. And so that would mean this also is O of rows. And this here, in the same way, it's O of columns. So you can see the total time complexity for this is O of rows for this one multiplied by columns for this one multiplied by the min of rows and columns multiplied by, again for this function, by rows multiplied again by columns. And so let's just check the case of a square matrix of size n, right? Just to get you a rough idea of how much it will take there, so that we can get a better understanding of the time complexity here. So that would be rows is n and columns would be n in that case. So min of n, that would be just n, multiplied by rows, that would be n, and columns, that would be n. So you can see we have 5 n's. So roughly this would be O of n to the power of 5, such that n can be the smaller of the two. At most, it will be the bigger of the two dimensions of the matrix, right? And so you can see this is a very big time complexity. So we should improve this. In terms of space complexity for this, we are not using any extra like array or something. We are just using this max length. So it's pretty good in terms of space complexity. But let's try to find a way to improve this time complexity. And so one way to think about this is, we have a matrix of 1 and 0s, and so if you try to think a little bit of, and what we are trying to do here is find all 1s. So one thing that is useful if we had an array of these ones, it would be, we would just, and we want to find out if there is only 1s in like some range, let's say this one. What we would have done is, let's just count the sum here. Like, let's say this is I and j for an array. What would be useful is, let's just count the sum of ij to j and check if that's equal to the length j minus I. That means we have only 1s, right? So the same idea we can do it for a matrix. So let's just take matrix sum of each of a square, and if the area is equal to, if the sum of the values in the square is equal to the area, which means the side multiplied the side length squared, then that means we have only 1s, right? But if it's less, then that means one of the element was 0, and so if it's less, that means one of the element was 0. was 0, so we should not consider it. So we should not consider it because we are looking for the largest one with only ones, right? And so from this idea, there is one thing to learn here is that whenever we have a problem on a matrix, we should think, what if it was an array? How can we solve that? And then try from there to apply that to 2 dimensions. And maybe if you had the 3-dimensional problem, same thing. But yeah, so that's the original idea. And so whenever we have for an array something that needs the sum in a range, we directly think about using prefix sums. Because if we have an array of prefix sums, then sum of I to j would be just prefix sums of up until I minus, so that involves all of this. Sorry, prefix sum up until j minus the prefix sum up until I, right? Up until I plus the number at I, right? Because we subtracted here. Or we could have also done something different, which is it's just that minus this for I minus 1, and that would contain I, right? So same thing. Let's take this idea and apply a prefix sum for the matrix. So if we had the prefix sum for the matrix, then it would be easy to find the sum of a square, of values in a square, and we will be able to, so sum of the prefix sum for the matrix to get to faster compute the sum of the elements in a square. And from there we can just check, then we can just check if that sum is equal to size multiplied by size, which is the size of the square. If it is, then do what we did here with max length, because that's a valid square that we should check, right? Which is just size here. And so this is the idea. And so now how can we, so we know this relation for the array, how can we find a similar relation for a matrix, right? So let's call this one relation 1, R1, right? So how can we find R1 for a matrix? Like if we have the prefix sum up until, let's say, position 2, 3, how can we find the sum from position 1, 2 to 2, 3, for example, right? Or if we have the sum from 1 to 4, 5, how can we find the sum that has top left corner 3, 2 and top right corner 4, 5? So you can see the same thing we are looking for here for the array, we want to find it for a matrix, right? And so, or a 2-dimensional array. And so one thing we can think of is that, so let me show you this drawing here. So with this drawing, it can be kind of clear. So let's say this is the top left corner right here. So this is xy, the top left corner. And so to find the sum of this square that starts out at the top left corner, xy, we can just find the sum of this entire thing, the entire matrix. So basically what we want is we want to find this sum in terms of only squares, sum that start from 0, 0. That's the idea. Because that's what prefix sum does. Like for the array, it starts from 0. For the matrix, it starts from this position 0, 0. And so to do that, we can take this entire sum, subtract this portion here, which is from 0, 0 to this position, which is y minus 1, right? It's y minus 1. Yep, 0 to y minus 1. And this yellow rectangle here, which is from 0 to x minus 1, right? Because this is here x minus 1 position. And then the problem is, since we subtracted this one and subtracted this one, using something called inclusion-exclusion principle, which means here basically, essentially it means that, well, we subtracted this part that is in common between the green rectangle and the yellow rectangle, we subtracted that 2 times. And so we need to add it 1 time to compensate for that subtraction. And this rectangle is just from 0 to x minus 1, that's this side, and its left side, its height side is from 0 to y minus 1, right? And so that's pretty much what this drawing here says. So this drawing says that the blue rectangle here, so the blue rectangle is just the large pink rectangle minus the long yellow rectangle minus the green yellow rectangle, and since this rectangle here we added 2 times, we subtracted it 2 times as part of the yellow and the green one, we need to add it 1 time to compensate for that. And so that's what the concept that we will be using. So let's write a formula for that then. So let's say for rectangle at with or not rectangle, sorry, square, sum for square at ij is just going to be equal to, let's call it S. Let's call it just S, right? So that would be the sums. So let's say the square at ij is of size k, or k, yeah. Let's say this size here of the blue square is k. So that would mean, so first I think I need to tell you how can I, so for the array to compute the prefix sum, we just take prefix sum of I minus 1 plus num I, right? But for the for a square, let's just write that. So how to find prefix sum of a matrix. So basically sums at ij, so I'm going to consider this to be sum of the matrix ending at I minus 1, j minus 1. This is just to make computations easier, right? So that means that this sum here is basically sum of the matrix starting at 0, 0 and ending at, so the same thing as the prefix sums for the array. So this here would be the sums at the left side, so that's I minus 1 j, plus the sums on the top, the sum on the top, which is I j minus 1, minus the sum at I minus 1 j minus 1. Why is that? Because we will, when we for a matrix, let's say this one, the blue one, so if we computed this entire portion, right, and I'm considering a portion here, so the new portion that I'm adding is this one, so I'm saying it's the entire thing here plus the entire thing here. But the problem is the thing in common between the two, which is here, I added it 2 times as part of the sum I minus 1 j and as part of the sum of I j minus 1. So I need to subtract it once so that I have only one part of it left, right? And then I'm having, so for this entire thing, since I computed the above part and I computed the left correctly, now I need to add this small portion that is new, right? And so that small portion basically is the matrix ij. But of course, since the matrix here we are counting the sums and it's a characters of 1 and 0, so it's 1 if that's equal to 1, otherwise it's just 0, we had nothing, right? So that's how we can compute the prefix sum for the matrix. Now how can we do what we said here, the calculation that we said here? So the sums S, that's just the sum of the large pink rectangle, pink square or rectangle, we don't know. So that's just the prefix sum ending at, starting from 0, 0, ending at this position here. What is this position? That's just x plus the size of the square, right? So x plus the size of the square, which is k, But we are going to do -1 because we are starting from 0, 0, right? So basically because of this, what we said here. And then y plus k minus 1. That's the definition, right? This position here is, this one is x, and so we need to add k to get this one for the x position, and we need to add k here to get the y position, right? And then, so that's the pink square. We need to subtract the yellow square. And so this one is the pink square, or rectangle. And then the yellow one is going to be from 0, right? This is the position 0, and the x position is going to be this one, which is just before x, so it's x minus 1, all right? So we know that it needs to, this, basically what we are looking for is this position here, and so its x is x minus 1, right? So its x is x minus 1, and its y is this here. What is this one here? That's just the entire up until x, up until y, which is here. So this is y, this position here is y, and then we will need to add the entire size of the matrix, right? The entire size, sorry, of the square, the blue square. So that's y plus the size of the square, and again we need to add do -1 because of this rule that we set here. So this is the yellow square, or yellow rectangle actually, sorry, let's just be precise here. And then we need to subtract the green rectangle, and so that is, we need this position, right? Because that's what the prefix sum count, from 0, 0 to this last position, right bottom corner. And so that's the x value of that is this one here. What is this one? That's just x plus k minus 1, right? So it's sums of x plus k minus 1. And what is the y position here? That's just this one here, which is just the one before y. So that's y minus 1. And this is the green rectangle. And now what's left is just to find this turquoise, this one. I'm not sure what this color is called. Is it called turquoise? Sorry. Yep, it's called turquoise. So it's just this turquoise color here. So that's this one here. So again, we are looking for the bottom right corner because that's where the prefix sums compute. And so that one is just up just before the x of this one, right? So x minus 1, and just before the y of this position here, so y minus 1. So it's sums of x minus 1, y minus 1. Right, so this here is the turquoise rectangle, or square, it may be, depending on the position. Okay, so now that we have the formula, we can just check if s is equal to k multiplied by k, then we can just do what we said here. Right, and that's pretty much it for the solution. There is slight optimization that we can do, which is, since we are considering all sizes, let's just start from the biggest size first, and if we find that that's a valid square, that's the largest we can find. There is no need to try smaller sizes, right? But if we didn't find that it's valid, we need to try smaller sizes, right? And so the optimization that we are going to do is consider iterate through sizes in reverse order. So that the if we found a valid one, we can exit early, pretty much. Yeah, and so that's pretty much it for this for the concept of this solution. And so let's just code it up. So I'm just going to leave the check here for the matrix and having the rows. we will still need to compute the prefix sums, so we need to compute the prefix sums. And then check for valid squares. So to compute the sums, let's just have the array, which is going to be initialized for 0 for all of them. And so we'll start out with the range of columns +1, and then for range of rows +1. Okay, and we need to start filling that, right? So in range of rows, and since we said just to avoid having to do some special check for I equal to 0, because we are doing I minus 1, we are just going to make this one start from 1, so that I minus 1 would be 0, and my prefix sum would hold the what did I say that? Well, yeah, ending at I minus 1, j minus 1, right? So that means rows +1 here, and for j in range of 1 and columns +1. And now the sum, I'm just going to apply what we identified here, which is this. But the matrix is actually I minus 1, j minus 1, since because of what I said here, it's ending at I minus 1, j minus 1, right? So this is this position actually. And then once we have that, we would have computed the prefix sum. And then now we can check for the valid squares. So that would mean just go through all the top left corners in the same way we did before in the brute force solution, but now we have an easier way to compute the sum, right? In just constant operation, right? So that would mean we are going to go through this in the same way we did before. And then we need to go through all the sizes in the same way again. So size is again the min of pretty much rows minus I +1 and columns minus j +1. And now we can check if it's valid easily using this sum computation. And so S is this. And now we can just check this to check if it's a valid square, instead of doing NO of n squared that we had to do before. And since here I didn't do that, but I said one optimization is to iterate through sizes in the reverse order. So to do that, we are going to start from this one, but we are going to end at 0 and subtract each time the size by 1. So go from the highest size and keep going to smaller sizes to get to check if it's a valid square. And the size is actually k. And this is actually no longer a size because it's the sum. So, and it's k multiplied by k, so it's the area. So let's just say this is max area. So this is max area, and we would have max area here, and at the end we can just return that. So you can see with this prefix sum calculation, we reduced the computation that used to take O of n squared to just take in constant time. Yeah, so that should be pretty much it. So let's run this. I think I have a 0 for that. Yeah. It's not x. I did I here, so ij. I minus 1, j, I minus 1, j minus 1. Okay, we have here it's returning 2. So there is a problem. I'm adding sk. I should be putting the sum, right? Okay, so that should be good. Submit. Okay, so we have a wrong answer for this one. Let's add it to the test case. Let's see what could be the problem. Okay, so we go through the rows and then the columns, and it's 1 if the matrix value is 1, otherwise it's 0, and we add the sum of I minus 1 j, I to j minus 1, I j minus 1, then we subtract for k. And then with this we go through all the top left corners possible. We get the size starting from rows minus I plus 1 to columns minus j plus 1 to get to the columns minus j, and we keep subtracting, and the sum is I plus k minus 1, j plus k minus 1, minus, so this is the big pink rectangle, minus the yellow one, which is I minus 1, j plus k minus 1, and then the green one, which is I plus k minus 1, j minus 1, correct, and then the turquoise one, which is I minus 1, j minus 1. So this one actually I shouldn't be subtracting it, right? This one I should be adding it, because if we look at the photos again, this is this one here, and this is the one we subtract 2 times, so we should be adding it, right? So that was my problem here, and so that means it should go as plus here. Okay. Okay, that looks right. Okay, so that passes. And as in terms of time complexity here, it's we have O of rows here, and we have O of columns. And then here, at most, it would be, as we said for the previous example, min of number of rows and number of columns. And this one here is same thing, O of rows, and this one is O of columns. So overall, it's pretty much rows multiplied by columns for computing the prefix sum. So that's the first part, plus O of rows multiplied by columns multiplied by min of rows and columns. And since if we do the same simplification we did before, which is considering it a square matrix, we would have n multiplied by n plus so pretty much this one, though, because this part is bigger, let's just divide it into, let's just so say this is pretty much just roughly in terms of big O is just rows multiplied by columns multiplied by the min of the 2. So if we take it as min, as n, simplify it to be n for a square matrix, that would be n by n by n, right? So so it's O of n cubed. So it's a lot better than the solution we had before, which was O of n to the power of 5. And in terms of space complexity, here we are still using constant space like this. No, sorry, we are not using constant space because we sacrificed that to get a better time complexity. So here we have this prefix sum where it's O of rows multiplied by columns, right? So roughly, if we do the simplification, it's O(n squared). So we gave up a little bit of space complexity to be able to improve the time complexity. So yeah, that's one way to solve this problem. There is an entirely different way to solve it using dynamic programming. So let's look into that. So the solution using dynamic programming comes from the fact that we say, okay, we are looking for the maximal square, the largest square containing only ones. So when we are looking at something that wants to optimize some largest or maximal or minimize, we need to directly think if dynamic programming can apply. And so for dynamic programming, we need to find a couple of things. What is our goal function? What is our state? What is our base case? What is our recurrence? What is our iteration order? Maybe sometimes we need that, sometimes it's just the default one. And so what is our goal here? It's to find the largest square containing only ones and returns its area, right? So we know that our state needs to have the largest square in it somewhere, right? Containing only ones. So what can be the parameters for us? So one parameter we can take is the top left corner of the square. One other parameter is the bottom right corner of the square. If you can, when you are solving this problem the first time, you can try all of them and see whichever one fits. But for this problem, the one that fits is the bottom right corner of the square. And basically, that would mean that dp of ij, that is our state, it's just the length. And since finding the square, like the size of the square, means just finding the length or of the side of the square, we can just simplify our dp state here to be the length of the side of the largest square of only ones ending at ij. And to do that, that's pretty much the state that we will be using. So the base case for that, so this means the length of the side of the largest square containing only ones ending at 0, 0, right? And so we know right away that this is equal to 1 if the matrix at that position is 1, right? It's only that cell. But if it's 0, then that's 0, right? And so it's this if this is equal to 1, otherwise it's 0, right? Now let's think about the recurrence. So if we have so essentially, if we have a square, let's say like this, let's take the example that we have here. So what we can be doing is construct our dp, right, and initialize it with this dp0. So our dp array would be like this. We can initialize it with 1, right? And so the rest is for now 0, because we will initialize it with 0 values, right? So we have 5, okay, 0, 0, 0, 3, 5, right? We need 5 of these. We need 4 on this side, right? Okay, and then it's just filled with 0 first. Okay, so when we computed this one and go here and go examine this one, for example, right? This one is 0. Whenever it's 0, the value just stays the same because it can't form any square. But when we are at this one, we can look at so all those actually on the top, since they can't form additional square ending at them because there is nothing above them, then we know that if the value is 1, then the square value is 1. Otherwise, it's 0, right? And so that makes it straightforward. The same thing for the left side. Since our dp state means it's ending at that position, we can't form anything left of it, right? We can form a tab, but we can't form it left of it. And so there is no way for a square larger than 1 to end there. And so their value would be the same as whatever value is in the cell. So that would be just like this. For the rest though, so for all those that are 0, like this one, and this one, those stay 0. But for this one, can we form a square that is ending at this position? So to decide that, we need to look at, because ending at this, we need to look at the one above it, the one to the left, and the one to the right, and see if all of them are 1s. That means we can extend and make a larger square ending at this position. But if any of them is 0, that means this one is going to be 0, because it has to, in order for the square to be ending at it, it has to contain the one above it, right? So it stays as 0. And so that starts telling us what the solution is. So we now right away we know that we need to examine the top left. So we need to examine the top cell, left cell, and top left cell. So pretty much that means that dp of ij, the square ending at that, the length of the side of the large square ending at that, it would be a function of the top cell, which is dp of I minus 1 j, and dp of the left cell, which is I j minus 1, and the top left cell, which is dp of I minus 1 j minus 1. So right now what we are trying to do is find the recurrence, right? So what's this function here? So we know that we are going to check if there is a 0, right? But let's see this case here, right? This case is 1 here. So this case is 1 because the left one is 0, so we can't find the square larger than 1 ending at it, right? And then the one bottom to it, the top left also is 0, so we can't construct a square ending at it. So it has to be only 1, the value itself. The one below that, that's 0, so that's just 0. Now what about this one here? So this one, it can't have a square ending at it because the one on top is 0, and so that one stays, that one becomes 1 because of its value. So it's a large square ending at that position of size 1. What about this one here? So this one, if we look at its top left, top cell, and left, top left, and this one, they are all 1s. So that's interesting. That means we can extend the square. How do we know by how much? So if we had only 1s here, that would mean, okay, we can extend by more than 1, but that's not the case. Here we have just this one, so we can extend by only 1. And so that means that the size of the squares that were formed is that size plus 1, so it's 2, right? And let's say if we had one larger and all those next to it were of size 2, that means we can extend that by 1, because now we can just add to that square from the left, from the right, and from the bottom, and make a larger one, right? And so you can get the idea of the function from this, because this basically means that we are taking the minimum, because that's what square is. All sides have to be equal. So if one is larger, one side of one's is larger than the other one, we can't use the rest because it has to be a square. And so this one would mean that it's dp of I minus 1, whatever the sides, the minimum sides of the other states, plus 1, because we are extending it with this new one as the bottom right corner, right? And so now we have our recurrence. Now in our iteration order, as you saw, I just went from the top left and kept going, because when I'm here, when I'm at some position, I need only the top one, the one top left and the one left. And so using this iteration order where it's from this to rows and for j from, I would be able to, when I'm calculating this, I'm sure all of these would have been calculated, right? There is only a slight change that we may need to make afterwards to make this I minus 1 not go to minus 1, but essentially this is the idea. So now we have all the data that we need for our DP solution. So let's just start coding that up. So first thing we are just going to do to get this check out of the way, check for size 0. After that, we are going to construct our DP and we need to initialize rows and columns, which would be length of matrix. So this would be columns actually, and this is for in range of rows. And now that we have this, we need to initialize the base case. And we can start doing our iteration. And let's use our iteration that we found here. We just need to check against the case where I equal to 0, because this one would be -1, so we don't want that. So we need to check if I equal to 0, and same thing for j for this case and for this case. So or j equal to 0, then we need to do a special handling, and that's what we said here for the top and left top corner and the left top row and the left column. It's just the values, whatever the values are, that's what we can form, because we can't go up and we can't go left. And the definition of our DP is that it's the length of the side of the largest square of only ones, right? So that would mean that DP of ij in that case would be just the same as the base case, right? So that actually tells you that we don't need to do this, because that would go to here and will compute the right value, right? So we don't need to do this specifically, and this is just this. Otherwise we can do like this. And we need to keep track of the max, whichever max we found as we go along. And so that would mean that would be max of length is equal to the max of, since dp of j is just the length of the side, so we just do max length and dp of ij. And at the end we take whatever max and we return the area, which is max length multiplied by max length. There's just one thing that I did here that I didn't check, which is I extend only if the value is 1. If the value is 0, I should just keep it 0, because that means the length is 0. There is no way to extend or anything. So if the matrix at ij is equal to 1, only then that I can try to extend. And that's pretty much it. That should cover it. So let's run this. Okay, that looks good, so let's submit. Okay, so that passes. In terms of time complexity, we have O of rows here multiplied by, for this loop, and then O of columns, and that's pretty much it. And so this is O of, if we use the same simplification that I said before, this is O of n squared. So you can see this is better than the solution I found before this one, which is O of n cubed. So we iterated from the first we had a solution that was O to the power 5, and then we found one to the power 3, and then with dynamic programming now we are able to do one that is just to the power of 2. So it's quite an improvement. For space complexity here, we are using only this array that is of size of rows multiplied by columns space. So it's the same space as the solution that we found that is cubed. This one is better because it has, in terms of space complexity, but the time complexity is just too big. So this is also with the simplification that we used O of n squared. So that's the dynamic programming solution. I would like to do a slight simplification to avoid this I equal to 0, which can be done slightly by changing what the state represents. So if we say this state represents ending at I minus 1, j minus 1, then that makes this simplification possible. So we can just make this size bigger by 1, and instead of starting from 0, that prevents us from doing just this one iteration, this one line of code. Instead we have to check for equal to 0. We prevent that by just going from rows. Why are we going to rows plus 1? Because since this one ending at I-1, j-1, to consider the last position, we need to end at n-1, j-1. We have to go all the way up until, sorry, to end at n to get n-1, n-1. Yeah, sorry, let me write this. To get to rows -1, columns -1, we have to do dp of rows, columns, right? And to do that, we have to do row plus 1, because that's the way Python's range works, is that it ends at, if you do this, it will end at rows, and so that's what we want here. So now I no longer need this, and I no longer need this here, and now because I'm doing this, if it's the cell is 1, these values are 0, and so by default it will be just 1. So it works out in the same way as before. And yeah, that's pretty much it. So let's run this. So yeah, I'm now considering it's ending at I-1, j-1, so it should be -1, -1. So yeah, it looks correct. Let's submit. Cool. Another improvement, but this time in terms of space complexity, because we have a quite big space complexity here of O of n squared, or O of rows by columns. And so how can we do that? So you can see here, if you look at the DP we are using, we are using only the previous row in the DP two-dimension array and the previous column, right? With this, so we don't need actually to keep track of all of these. And so when we see that we need only the previous row and previous column, so let's just keep track of 2 rows instead. So that means let's just keep track of the previous row and the current one. And so those would be initialized to 0. So in range of rows, and let's keep track of the ones for 0 for in range of columns, right? And so that would mean that here I can just fill the current row, right? So I just need to fill the current row. What is this one? So this is the previous row value at j, right? And so the previous row value at j, that's just previous j. So what is ij-1? This is just the previous column in the current row, because it's I, right? So this is pretty much the previous column in the in the current row, so that's current j-1. So what is this? This is the previous column in the previous row, so it's previous of j-1. And yeah, so that's pretty much the only thing we need to do. And this is current j. Since I'm starting from 1 here, though, I need to do this is columns plus 1 and columns plus 1. And yeah, so that's pretty much it. Let's run this. Okay, so that's definitely wrong. Let's see where. Yep, so the problem is I'm using the previous row, but I never put values in it. And so when I'm done with processing a row, I need to save it in the previous row so that the next row can use that. And so what should happen is that here I need to say this one is the current row in this iteration. This becomes the previous row. And the current row, I should replace the values so that they don't get used again. So I should replace them with using the initial value. And that's pretty much it. Okay, that looks working. And that's that works. And so the time complexity is the same. We didn't change that, but the space complexity here, we improved it by, before we were using O when squared or rows by column. Now we are just using 2 multiplied by columns. And so it's roughly, if we use the simplification, is 2 of n. So, or let's just say this is O of columns pretty much in terms of O. And so if we use the simplification that we did, it's just O of n. So you can see it's a lot better. Okay, I think that's pretty much it. That should be okay. Yep. So there is another way to even improve the solution faster, to get rid of these 2 columns and to have just one using 1 row. But yeah, in terms of O complexity, at least it doesn't matter here. So I'm going to leave that for now. And that was it. Thanks for watching, and see you next time. Thank you. Bye.